Hello everyone, we are here to present our ANN final project on spam email classification. This project represents a deep dive into natural language processing and deep learning to solve a critical cybersecurity challenge. Let's start with the big picture. Our goal was to build an automated system that doesn't just look for keywords, but actually understands the context of an email to detect spam. Our solution uses a long short-term memory (LSTM) neural network. We trained this model on approximately 5,700 emails, and as you'll see, we achieved a system that is highly confident in distinguishing between legitimate ham emails and malicious spam. So why is this necessary? Email remains the primary entry point for cyberattacks like phishing. The problem with older spam filters is that they rely on static blacklists or simple bag-of-words models. These struggle when spam becomes sophisticated and mimics natural language. Our solution implements an RNN variant, specifically LSTM. By treating email classification as a sequence modeling problem, our model can differentiate context. It knows the difference between winning a prize in a lottery scam and winning a game in a casual conversation with a friend. Every good model starts with good data. We utilize the spam mails dataset from Kaggle. The dataset contains about 5,700 samples, labeled simply as 0 for ham and 1 for spam. To ensure our results are reliable, we split this data. 80% went into training the model, and we held back 20% for validation and testing. This ensures that the metrics we report later are based on data the model had never seen before. Raw text can't go directly into a neural network, so we built a pre-processing pipeline. First, tokenization. We converted text into sequences of integers. We restricted our vocabulary to the top 5,000 most frequent words to remove rare noise and keep the model focused. Second, padding. LSTMs require fixed-length inputs for batch processing. We standardized every email to a length of 150 tokens, padding shorter ones and truncating longer ones. This is the engine under the hood. Our model uses a sequential architecture built in TensorFlow/Keras. The embedding layer, this transforms those integer tokens into dense vectors, capturing the semantic relationship between words. The LSTM layer, with 64 units, this layer captures the long-term dependencies. It remembers the start of a sentence while reading the end, which is crucial for context. The dense layer, finally, a sigmoid activation outputs a single probability score between 0 and 1. For training, we use the Atom optimizer and binary cross-entropy loss, which is standard for this type of classification. However, we hit a hurdle. During our initial training runs, we noticed a problem around Epoch 4. The model started memorizing the training data instead of learning patterns, a classic case of overfitting. We needed a way to stop this degradation. This graph visualizes that instability. If you look at the orange line, our validation accuracy, it peaks at Epoch 3 and then crashes downward, even though the training accuracy keeps going up. This divergence confirms overfitting. The solution? We implemented early stopping. This technique monitors validation loss and automatically halts training when improvement stops. It effectively rewinds the model to restore the weights from Epoch 3, giving us the most robust version of the model. So how does it perform in the real world? The model shows strong polarization, which is exactly what we want. It rarely sits on the fence with a score of 0.5. For a clear spam example like urgent, your account has been compromised, it gave a 95% probability. For a ham example like a meeting reminder, it gave a 2% probability. This high confidence makes it very reliable for automated filtering. Slide 10, conclusion. To wrap up, this project successfully demonstrated that LSTM networks are highly effective for text classification. The embedding layer allowed us to capture word meanings, the LSTM handled the sentence structure, and early stopping ensured our model remained generalizable. We have a robust system capable of high-precision detection. The project was developed in Python using Google Colab. This ensures that our results are reproducible and cross-platform compatible. We relied on the standard stack of TensorFlow, Keras, Pandas, and scikit-learn. And that's it. Thank you for your attention.